Welcome to AI Paper Swap, where we break down the latest AI and tech papers for researchers and ML engineers. Today, we're looking at a June 2026 paper titled Echo Memory, a controlled study of memory and action world models from researchers at JD's Joy Future Academy, HKU, and others. Here's the core insight right away. Action world models are great at generating video, but they are terrible at remembering what's behind the camera when it turns around. The researchers built a tightly controlled matrix to test different memory architectures and found that our standard metric for measuring memory replay, PSNR, is fundamentally flawed. Methods that perfectly reconstruct a camera trajectory often completely forget salient objects when the camera leaves and returns. Ultimately, they discovered that deeply integrated blockwise state space recurrence and raw context are, well, the only reliable ways to preserve semantic memory, while aggressive spatial and hybrid compressions just completely fail the test.
Yeah, and to put that in context, this is the silent change problem you just mentioned is really the central frontier of video generation right now for anyone building these models. I mean, we've moved past just making a plausible 3-second clip.
Right, the standards are way higher now.
Exactly. The real goal is producing a controlled, consistent world rollout over a really long horizon. So when the camera pans away and returns, and the scene is shifted, or a salient object has become an imposter, that is the ultimate test. It's a catastrophic memory failure.
And we know memory is broken, but I guess why did we need the specific paper to tell us how to fix it? Because, as the researchers point out, previous claims about memory improvements are basically impossible to verify.
Yeah, the literature is completely entangled. I mean, every month there's a new paper claiming, state-of-the-art memory performance using some new module. But you have no way of knowing if the gain is from the memory itself or because they changed the video diffusion backbone or tweaked the retrieval policy.
Or the training schedule, right?
Exactly. Or the prompt budget. It's all mixed together.
It's like reading previous literature is basically trying to evaluate a new car engine, but the manufacturer also changed the chassis, the tires, and the racetrack all at the same time.
That is exactly what it's like, which is why the echo memory solution is so necessary. They built a highly rigid control matrix. They locked down the backbone entirely. They used a pre-trained video diffusion transformer, or DIT.
Okay.
And they standardized the flow matching setup, the data interface, and locked the camera action representation to this 12-dimensional relative RT vector. The singular variable they allowed to change was the memory profile. So what is stored, how it's compressed, and how it's read out.
But wait, let me push back on that for a second. By freezing the DIT and the action encoding, aren't we unfairly limiting memory architectures that maybe, might actually need a specialized backbone to shine?
It's a fair question, and the scope is intentionally narrow. But it's necessary to separate the 4 axes of memory that the field just habitually conflates, which are capacity, compression, readout, and recurrence. If you let the generator evolve alongside the memory module, you're measuring system-level engineering. You're not doing memory science anymore.
Makes sense. You have to isolate the variable. So once the test environment is perfectly controlled, how do you actually score the memory? Because the paper reveals that the field has basically been chasing the wrong metric this whole time.
They absolutely have. The authors expose this using a 3-branch protocol. So branch 1 is replay quality, which is reconstructing a ground truth camera trajectory. And they measure that with standard metrics, PSNR, SM, LPFPS.
Right, the usual suspects.
Yeah. Then branch 2 is an in-domain loop revisit. Basically a 180-degree loop backed by ground truth. But branch 3, this is the big one, is the open domain return probe. It's a 45-degree leave and return excursion.
And because it's an open domain excursion, there are no ground truth pixels, right? Like, you can't calculate PSNR for that.
Exactly. So they had to get creative. They used Qwen Edit to insert distinctive identity anchor objects, like a rainbow teddy bear, into held-out environments. And then they use a vision language model, Qwen3VL, as an automated judge to verify if the scene, the viewpoint, and that specific rainbow teddy bear actually survived the camera panning away and panning back.
Oh, wow. So a VLM judge for the return probe. And the big revelation here is that the branches routinely disagree. Like, high replay PSNR does not mean high open domain VLM scores.
They aggressively disagree. A model can score incredibly high on replay PSNR and completely fail the open domain test.
Wait, if a model is flawlessly reconstructing the ground truth pixels in a replay trajectory, shouldn't it inherently have, like, a perfect memory of the environment?
You'd think so, but it's an illusion. It's the crutch of local visible support. For in-domain trajectories, the model is just leaning on familiar textures and local geometry. It looks like memory, but it's really just hyper-optimized local extrapolation.
Ah, so it's cheating, basically.
Basically, yeah. The open domain return probe actively strips away that local support. It forces the model to regenerate a highly specific object entirely from its internal memory representation because the object dropped out of the context window entirely.
That makes a lot of sense. So let's look at the architectures that failed this open domain test, because understanding why they failed really shows how optimizing for token efficiency can just destroy a world model.
Right. Let's talk about spatial memory failures. This is where you store compact scene tokens on a spatial grid. These architectures absolutely dominate the replay PSNR metrics. But on the open domain VLM test, they completely collapse. I mean, scoring a dismal 6.00 out of 100.
A 6? That's barely anything.
It's terrible. And the researchers proved how hollow this is with a storage versus readout ablation. They tested withholding the readout completely and inject none setup.
Wait, so the main network couldn't even see the memory grid?
Exactly. They completely severed it. And shockingly, replay PSNR actually improved when the memory was withheld.
That is wild. So the model did better at pixel reconstruction when it couldn't access its own memory.
Yes, because it proves that sometimes a spatial memory module is just acting as a regularizer for the network.
Yeah.
It's not functioning as usable memory at all. Even when they added a dedicated cross-attention readout, it only hit 17.12 on the VLM test. The grid encodes roughly where things are, but it completely loses what they are.
It has the layout, but no semantic details. And the compression failures are just as bad, right? You'd normally think, more frames means better memory.
Right. But they found that aggressive length, compression-like, dropping 3 out of every 4 frames, so R equals 4, actually beats weight-only compression, where you keep all the frames but just rely on attention to reweight them.
Because with weight only, you're spreading the attention budget too thin across a bunch of redundant frames.
Exactly. The signal for the identity anchor just gets completely diluted.
But what really stood out to me was the hybrid disaster. When you combine length pooling and token weighting in the same model, the open domain performance just craters to single digits.
It's a fatal order of operations. Think about it mechanically. The pooling averages out the frames first, before the model can even decide if they're important.
Oh, I see.
Yeah, so it destroys high-entropy identity anchors, like our rainbow teddy bear, and turns them into a muddy representation before the weighting mechanism can even see them.
So it's like blurring an image and then trying to run an edge enhancement filter on it. The data is already gone.
Precisely. The semantic evidence is obliterated before the cross-attention layers can even access it.
Okay, so if compact grids act as hollow regularizers and hybrid compression destroys the token budget, what actually preserves the world state?
Well, it comes down to raw capacity and deep structural recurrence. The raw context baseline is just an absolute powerhouse. There's no compression, no spatial mapping, just feeding raw previous frames into the context window.
Right, and moving from k equals 1, so just the anchor, to k equals 5 jumps the open domain VLM score from 12.25 all the way to 50.75.
Yeah, and pushing it to k equals 20 gets you to 58.63. The gain is massive for semantic return. But what's fascinating is that scaling that context barely moves the needle for replay PSNR.
Which again proves they're totally different mathematical capabilities. But we can't really use k equals 20 raw context in production, right? It's way too computationally expensive for long horizons.
Exactly. The attention overhead is too high. So this is where implicit state space memory, or SSMs, come in. The researchers tested a legacy hybrid SSM, which is basically a lightweight gate around attention, versus a blockwise SSM, where the recurrence is integrated deeply into every nth DIT block.
And the divergence in the results there is huge.
Massive. The legacy SSM gets great in-domain PSNR. But the blockwise SSM achieves a massive 69.00 on the open domain VLM test. It beats even the k equals 20 raw context.
That's incredible. But it suffers on replay PSNR, right?
It does, yes.
It's almost like I compare the blockwise SSM to a brilliant but really messy student. Like their immediate notes are sloppy, which is the bad replay PSNR. But because they deeply integrated the knowledge during the lecture, they completely ace the final exam where they have to synthesize the concepts from memory, which is the open domain return probe.
I love that analogy. It's spot on. The legacy SSM is just rote memorizing the current page. Finding 4 in the paper really emphasizes this point implicit memory isn't just some generic switch you turn on. It has to be structurally deep enough that the network physically cannot bypass it when the camera leaves the visual support.
The latent state has to accumulate evidence, which forces compression and lowers immediate pixel fidelity, but saves the semantic identity.
Precisely.
So to summarize this massive quality time trade-off we're left with, we can't just throw k equals 20 raw context at every model because it's too expensive. But we clearly can't use current spatial memory because it causes literal amnesia and fakes its metrics.
Right. And the real call to action here for the ML engineer listening is when you read the next paper claiming a quote-unquote new, highly efficient world model memory, you absolutely must demand to see open domain return metrics.
Not just replay efficiency.
Exactly. Replay efficiency is dead as a standalone proof of memory. If they don't test semantic return, they're just measuring temporal interpolation.
They need to prove the rainbow teddy bear survives the pan.
Yes, exactly.
And I want to leave you with a final, really provocative thought to mull over based on these findings. Since replay and semantic return scale so differently and basically penalize each other, what if the future of action world models isn't a unified memory module at all?
Oh, you mean decoupling them entirely?
Exactly. What if we need a split brain architecture? You could have a cheap, lightweight spatial grid dedicated purely to short-term geometric replay. And then, running completely parallel to that, a deep, blockwise state space pathway that acts purely as a semantic anchor for long-term object identity.
That is a fascinating idea.
Yeah.
You'd essentially be separating the physics engine memory, for spatial trajectory from the object permanence memory.
Right. Let the spatial grid handle the immediate geometry and let the deep recurrence encode the persistent state of the world. It feels like the logical next step.
It really does. It's a massive paradigm shift in how we build and evaluate generative video.
Absolutely. We'll keep building, keep testing those return pros, and we'll catch you on the next deep dive.